On our Polar Curves Day 1, we're going to be looking into polar coordinates and trying to find another way to represent a point. There are other ways to represent points than with what we call Cartesian coordinates. Now, Cartesian coordinates, also known as rectangular coordinates, are really the coordinates we've been using to plot points all the way through pre-algebra up to now. We have an x comma y. X is your horizontal distance, y is your vertical. You can move left, right, up, down and arrive at a point. But there are other ways we can do that. Today we're learning polar coordinates. Polar coordinates, we first identify the origin as the pole, the positive x-axis is an initial ray of an angle, and we are going to have polar coordinates. They're going to look just like ordered pairs. However, they are representing r and theta. R gives the directed distance from the pole, from the origin, to the point in question. Theta gives the directed angle in radians from the initial ray, which is on the x-axis, positive x-axis, to the point. So consider what we know to be the point 2, 2. This is your Cartesian or rectangular coordinate. We'll go 2 steps right, 2 steps up. And we, of course, could create a triangle. We could see x is equal to 2, y is equal to 2. Here, r is the distance from the pole, from the origin, to this point, P. Now, of course, very, very quickly, if we remember our geometry, we're going to remember that in a 45, 90 right triangle, the two sides, the two legs are congruent. We have a, the hypotenuse is a radical 2. So we would be able to know that r is 2 root 2. We'd also know that our angle down here is 45 degrees. Of course, we could also have used the Pythagorean theorem to help us find r, and we're going to talk about that later. If you wanted to find this angle theta, and we can write this out, the tangent of that angle would be opposite over adjacent. But in any event, a polar coordinate that we could have would be r comma theta, but we need to write theta in radians, 2 root 2 and then pi over 4. Well, notice it says list 4 polar coordinates for this ordered pair. We could also have an r of 2 root 2, but we could move in an angle that goes in a clockwise direction, and of course this would be going in a negative direction. You can see that we're going to be at negative 7 pi over 4. We're going to be just shy of negative 2 pi. Well, maybe the biggest adjustment with polar coordinates is dealing with this issue that we can have a negative r. The negative r value is getting tied into this directed distance, and I'm going to say r is equal to negative 2 root 2. When you're using a negative r value, we're always going to be working from the opposite quadrant from where the point is located. And of course, we're going to project that point to the quadrant that we want to land in. We're still going to maintain the same reference angle. So we'd still have a 45 degree angle made by the positive x-axis and this r length. So we could see that if we went pi over 4 past pi, we'd be at 5 pi over 4. Similarly, if we were to go in a negative direction, you could see that we'd be falling short of negative pi, so we'd be arriving at negative 3 pi over 4. But again, what are we seeing? Negative r values may be used to represent a point. However, we have to move to the opposite quadrant to be able to represent it. The angle in question will always be found in essence 180 degrees or equivalently pi radians away from the original point. So let's take a look real quickly at finding rectangular coordinates given polars. Here's r theta. Look at this. We have pi over 2 radians would be up here, and of course we're going to move 4 units away from the origin, away from the pole, to represent this point. How would we represent Cartesian or rectangular coordinates? Well, to get to this point in question that's 4 units above the pole at pi over 2 radians, you will move no units right or left, you'll just move 4 units up. And that would be your Cartesian coordinates, rectangular coordinates. Look at -3 pi. Now, pi, of course, is right over here on the negative x-axis, but with this -r value, we get projected to the opposite quadrant. Of course, right now, we're going to see that our opposite quadrant wouldn't even apply. We'll just have to move in the opposite direction of our axis. We are moving 180 degrees away. So we're going to be on the positive x-axis now instead of the negative. We're going to have 3 units here. So this is r equals 3. R equals -3, of course, means project in the opposite direction. Well, we land 3 units from the pole. How do we represent this point? We'll go 3 to the right. Do not move up or down any. That's your rectangular coordinates. Very quickly, let's take a look at C. As we look at letter C, we see a negative radius, a -r. And 5 pi over 6, of course, is going to be over here in the second quadrant. Now, 5 pi over 6, of course, has a pi over 6 reference angle. And if my r is -16, like we were just saying, that means we have to project. Let me fix that up. We have to project to the opposite quadrant. So we're going to be over here, r equals 16, with the same reference angle. Reference angles are always going to be maintained. Now again, something to help us out. We might wonder where our x and y are. Certainly we may use trig, but a good review of geometry would be very appropriate here. Pi over 6, of course, is equivalent to 30 degrees. We have a 30, 60, 90 right triangle. Opposite of 30 is A. Opposite of 90 is 2A. Opposite of 60 is always A root 3. So if 2A is 16, 1A is 8. And this side opposite of 60 degrees is 8 root 3. So we can see that we're moving 8 root 3 units to the right. We're going to move down -8 units. So that's where our rectangular units are located. Very quickly, let's take a look at 2a, 0, -4. Well, they want 4 different sets of polar coordinates. In other words, we are starting with rectangular. 0, -4 means don't move right or left any. Just go down 4 steps. And this is where our point is located. Very quickly, I hope something really jumps out. We obviously are having a radius of 4. R is 4 units away from the origin. So how could we write this out in polar coordinates? Well, my distance from the pole is 4. Down here, we could say we're at 3 pi over 2 radians. Now that's with a positive angle. We could also represent this with a negative angle of -pi over 2. You might wonder, well, wait a minute, couldn't we also have a -4 and a -4? You bet. But of course, negative r's would mean that we have effectively been launched to the opposite quadrant That's where r equals -4 is. Of course, here we don't have a quadrant. We are on the negative y-axis. Now we're on the positive part of the y-axis. But the angle up here would be pi over 2. So -4 comma pi over 2. Of course, that negative r value projects down to the point that we began with. We could also say, well, how could we represent this angle in a negative sense? Well, coming around from the x-axis, positive x-axis, going clockwise, we would see we'd be at -3 pi over 2. Real quickly, 1 comma root 3, well, we're going to go one step to the right, and we're going to move up root 3. But once again, if we paid attention to the 30, 60, 90 right triangle, we might remember a root 3, and 2a. We can definitely also use trig and the Pythagorean theorem to help us out. But hopefully we'd know that this is our a is equal to 1. This is a root 3. 2a is obviously just going to equal a 2. So my r is 2. And if we do some quick work here, we know that this angle would have to be 60 degrees. 60 degrees right across from its a root 3. But 60 degrees is pi over 3. So we have 2 comma pi over 3. That's working in a positive angle measure. From a negative angle measure, we'd have 2 comma -5 pi over 3. We could also speak about having a negative r value. If r was equal to -2, we'd be down here. And of course, we'd have the same reference angle of pi over 3. So in a positive sense, positive angle direction, if we were going into the third quadrant, we'd go past pi, and that would land us at 4 pi over 3. We could also work in a negative angle direction. That would be -2 pi over 3. So here are ways we can represent the point 1 comma root 3 4 different ways. All of those forms are representing this point that I'm going to highlight right now. This point that with x and y we call 1 comma root 3. Alright, real quickly, let's just take a look at how we could use our calculator to help us out with some of these. I'm not really even asking that we're going to go through work to make a graph as much. Change your mode to polar, keep everything on radians, and r would equal 4 sine. Now when you hit x, you'll actually get theta. Hit window, and usually the basic setup's from 0 to 2 pi, and we'll keep that. But in terms of our x, let's change everything to maybe 4.5, -4.5, and +4.5. Sometimes kids are wondering, why are you doing that? Well, I think it can be very helpful, because if you look at just going back to what r is equal to 4 times sine. The largest sine can be is 1, and 4 times 1 is 4. That means the maximum distance from the pole, from the origin, would be a 4. And that's effectively what I'm doing here. I'm just giving it some more work, some more room, excuse me. When you hit graph, you get a shape that looks something like that. Alright, well, let's move this over a little. Sine of 6 theta. Let me delete this. Just real quickly type in 6 theta. And the biggest sine can ever get is a 1. So I'm going to change this to -1.5. Down here, we'll make that a 1.5 also. We'll make this -1.5. And then change down here to a 1.5 also. Hit graph, and you will see a 12-petaled rose. Wow. Very nice looking shapes that you could be making here. We're going to stop for right now and come back and finish up this other graph in just a minute.